Hi, I am Rajat Chandna and I would be presenting my analysis on forecasting daily average traffic volume on westbound I-94. So first, let's go over the problem statement or the use case. That is, our client operates a big gas station with convenience store on a prime location on westbound I-94 and wants to know the expected hourly or daily average traffic volume passing through the westbound I-94 in order to develop an accurate demand forecasting model for its gasoline and food supplies. So in order to accomplish this task, the dataset was taken from UCI machine learning website. The data was collected hourly from one of the traffic stations located on westbound I-94. Data was collected from 2nd October 2012 to 30th September 2018. So approximately 6 years of hourly traffic volume data was collected. Also, other features that are included in the dataset are hourly temperature, hourly rains data, hourly snowfall, hourly cloud cover, and other weather-related features, and our target variable, that is traffic volume. Looking at the snapshot and the summary of the dataset contains around 48K hourly recorded observations with 9 attributes. As we can see that weather main and weather description features are more text-based fields, these would not be used in the current analysis. Looking at the realization of first 1,000 observations, we can see that series for the hourly traffic volume appears to be non-stationary with possible seasonal component. This is in line with our intuition since traffic is expected to be more during the daytime and business hours as compared to the nighttime, and this behavior is expected to continue into future. Looking at the ACF and spectral density plots, the series appears to have a period of 24 hours. This is again expected as traffic volume at 9 a.m. on Monday is likely to be correlated with that on 9 a.m. on Tuesday. Now looking at the quality of the dataset, on surface the dataset appears to be complete as can be seen from the outputs of complete cases and is-any functions, but a closer look reveals that there are time gaps present between some subsequent observations. Further investigations revealed that around 60% of the observations between observation number 15,000 and 30,000 are missing. Such high number of missing observations can severely interfere with the correlation structure in the time series. Hence, the decision was taken to average out hourly values to daily values. This would decrease the number of missing values in the data and still provide enough data for the analysis. Also, a new feature called isWorkingDay was created by combining the feature holiday and weekend or weekday. Now, looking at the realization of the created daily average traffic volume data, it can be seen that nearly 1 year of data still remained missing between mid-2014 and mid-2015. Imputing this missing data with forecast could severely bias this data set as large number of consecutive observations are missing. Also, it would require forecasting the explanatory variables as well. Enough recent data is present to make the useful forecast into the future. So based upon the above assumptions, the decision was taken to discard the data before mid-2015 and perform the analysis on the remaining data. After discarding the data before mid-2015, 9 observations still remained missing, and these were imputed by overall mean of their respective features. Now the dataset is ready for the analysis, and we will start with the univariate correlation-based modeling. The ACF reveals that there could be a strong weekly seasonality of s equal to 7 present in the data series. This is also corroborated by the presence of peaks near frequency 1/7 and its harmonics, as can be seen from the spectral density plot. Further investigation using the bandpass filtering and the ACF reveals that a long-term seasonality of 52 weeks or 364 days could also be present in the data series. Hence, the decision was taken to model this long-term seasonality first and then model any remaining short-term seasonality later. Even after removing the long-term seasonality of 364 days, the residual series appears to be wandering and non-stationary, and hence further differencing could be required. After differencing the series again, the residuals appear to be stationary but still doesn't appear to be white noise, hence modeling these residuals with ARMA model next. Both AIC and BIC scores identified ARMA 2-1 for modeling these residuals. Visual inspection of ACF of the residuals from this model and the results of the Young box test suggest that residuals are now sufficiently white. So the final univariate model identified for modeling this daily average traffic volume series is found to be ARIMA 211 with S is equal to 364. Next, we will look at forecasting performance of this seasonal ARIMA model. Last 28 days forecast from this model appears to follow the actual last 20 observation fairly closely. This model is slightly over-predicting at certain points, giving this model an overall ASC of approximately 28.5K. Now, forecasting into future for next 28 days using this univariate model, since our client has suppliers that require a minimum lead time of 4 weeks or 28 days to turn around and deliver the desired quantities of gasoline ordered. Next, it was assumed that things that were remained unexplained by the univariate correlation-based model could be explained by adding additional features into the model. Hence, a multivariate model could be needed. So, to investigate these possibly lagged multivariate relationships, a VAR model was created between daily average traffic volume and daily average snow and rain data. Last 28 days forecast from this VAR model also tend to closely follow the actual 28 days traffic volume data. But unlike univariate model, this model tend to underpredict at certain points, giving the model slightly more ASC of approximately 36.5K as compared to 28.5K of univariate model. Next, a neural network-based model was created to forecast daily average traffic volume with time trend and daily average temperature as exogenous variables. Similar to univariate and VAR models, the last 28 days forecast from this multi-layer perceptron model tend to closely follow the actual values. This model fit was slightly better than the VAR model, giving the model overall ASC of 30.8K. Finally, an ensemble model was created by taking simple average of the forecast from all the three previous models. The idea was that averaging will balance out slight overprediction by univariate and MLP model and slight underprediction by the VAR model, thus lowering the overall ASC and providing a more accurate forecasting model. And indeed, looking at the forecast from the ensemble model, this model was able to lower the ASC by at least 5K from the last best found model and achieved an overall ASC of 23.6. Hence, ensemble model was found to be best forecasting model for this series in terms of ASC. Thank you.